Hi everybody, welcome back. Thanks for joining. Today we're going to be continuing with Chapter 6, Newton's second law, doing some examples, continuing with the example of Jack and Jill and the pail. And this we have right in front of us right here. And as the old story, the nursery rhyme goes, they've got a pail of water and they're both holding on to it. So I'm going to take this drawing right here and I'm going to draw it a little bit more simply and a little bit larger up here, so we can see it. Okay, and Jack and Jill both holding on to it. They can't both hold on to it straight up and down. They hold it at kind of an angle. So Jill, no, which one is Jill? Jack is, let's see, Jack is force 1. So this is Jack right here. I'll make that in, I don't know, green. Okay, force 1, and Jill, I'll make her red. And that'll be force 2 right here, pulling up at different angles, okay? Now, one thing we're told is that the angles, well, the angles at which we're measuring these from are from the vertical. Like usually when you hold a pail, you hold it so it's straight down, so it's vertical. Well, these guys are holding it at kind of an angle this way and that way. So you'll notice that the angles that are being measured are actually from the vertical right here. So here's the vertical, and we're told that Jill's angle, and we'll go back to red again for Jill. I think that's red. That's 28. Oops, not 280. 218 degrees right there from the vertical. This is going to be really important because we're used to measuring angles from the horizontal. It's not going to change anything tremendously, but we just need to remember this, and I'll point that out a little bit later on. Jack, go back to Jack right here. In fact, no, I don't want to do that. Go back to green. And this right here, this angle theta, we'll call it theta 1 because it's Jack's angle. It's Jack, he's force 1. We don't know what that is, so we want to find out what that is. So we don't know what theta is right there. Jill makes 28 degrees with the vertical. Jack, we don't know what his angle is, but we do know the forces that they both exhibit, or they both exert. Jill's force, and I realize my red isn't quite perfectly red here, but that's okay, is exerting 11 newtons, okay? 11 newtons right there, and Jack has a force of 7 newtons. At some different angle from Jill's right there. Now, one other thing we need to remember is that these are not the only two forces acting on this pail. If they were, the pail would just shoot up into the air. Well, we are going to find out that it is moving upward, but we do know there is one other force acting on this pail, and this is the force due to gravity, or we might call it its weight force. So let's see, I'll make that blue right here, and we'll call it FW, okay, it's weight force. Now, we're going to talk more about that weight force a little bit later. But the weight force can be written as, well, what Newton's second law tells us, mass times acceleration. The mass of the pail times the acceleration that it's exposed to, in this case, that would be the acceleration of gravity. So whenever you have the weight force, that is the force caused by the weight of an object, you can always set it equal to mg right here. That is the object's mass times the gravity that it's experiencing. And if we're talking about Earth, it's probably going to be 9.81 meters per second squared. Okay, these are the three forces that are acting on this pail. Now let's read a little bit more about what it's asking us here. At what angle theta, so right here, what angle theta should Jack, with respect to the vertical, should Jack exert his force if the pail of water has a magnitude of 12.8 newtons? Well, this isn't really part of Jack's angle. This is really just telling us the weight force is 12.8 newtons. But what it's really saying is, at what angle should Jack exert his sideways force such that, and this isn't really clear, and I should clarify it, the pail will accelerate upwards. What we mean by that is it accelerates upwards only. It doesn't accelerate left or right at all. So this right here, in fact, I'm going to I'm going to underline that in something more obnoxious. The pail will accelerate upward. You might say upward only. Upward only. Only. So what this is saying is that there is no net force in the x direction. We can say that the net force in the x direction is 0 newtons. That's important because if there was a net force this way or that way in the x direction, the pail would slosh side to side. This is saying that it's going to accelerate upwards only. That's the idea. Jack and Jill want to both exert a force at 2 different angles and 2 different forces at 2 different angles, but the pail is going to move straight up. That's what A is asking us right there. After that, B, we're going to find the acceleration that it is moving upwards. Okay, so we have these two forces right here. One at an angle that we know, the other one that we don't know. Now what we're going to need to do then is take these forces at some angles, and break them into x and y components. So that's the next thing we're going to want to do. In fact, I'm going to take this right here, and I'm just going to move that over a little bit so it's out of the way. And then what we're going to do is we're going to set up a table. We're going to set up a table where we take our force 1 and force 2 and break them into x and y components. So let's do that right now. So we have our vector or our force, the magnitude, the direction theta, the x component, and the y component. And I'm writing them a little bit higher up there because I'll tell you why in just a second. We want to write the actual equation to get the x and y component. And you're probably saying to yourself, yeah, but I know how to get x and y, cosine and sine. But remember, we have our angles that are based off of the vertical. So when we get to that point, I'll clarify. What vectors do we have here? We got force 1, which is, I'm not going to write in colors anymore. Force 1 is green, but I'm just going to write it in blue. Force 1 and force 2. Okay, now the magnitude of force 1 is 7 newtons. Right? The angle, we don't know. We don't know what theta is. Force 2 is 11 newtons at a 28-degree angle. But again, be careful. It's 28 degrees from the vertical, which means when we find our x and our y, the sine and cosine are going to be flipped. They're going to be flipped. So to find our x, it's going to be magnitude it's usually cosine. Magnitude sine of theta, and our y is going to be magnitude. I'm writing too many bumps in and magnitude cosine theta. Again, see why we're doing that? Because we're not measuring these angles here from the horizontal. No, we're measuring it from the vertical, and so that means from the vertical, our x is going to be found using the sine. Our y is going to be found using the cosine. So what are our x and our y's? Well, our x component for vector 2, x and y we can find because we know the angle and the magnitude, right? For vector 2, that's going to be 5.16 newtons. So it's 11 sine 28, 5.16. And y is going to be 11 cosine 28. That'll be 9.71. 9.71 newtons. Okay? Now, let's go back here for a minute. We don't know really much about vector 2 because we don't know the angle. But we do know this. We do know all the way over here on our left that the net force in the x direction is going to be 0. Which means force 1 in the x direction has to be equal to and opposite to force 2 in the x direction. Well, we already know what force 2 in the x direction is. That's 5.16 newtons. So if there's going to be no horizontal force at all in the x direction, and that means force 1 in the x direction is going to be negative 5.16 newtons. See how we got that? There's no horizontal motion of the pail. So that means these two forces in the horizontal have to be equal and opposite. All right, well, then if we know, in fact, I'm going to erase those again. If we know then what the x component of vector 1 is, and we know the magnitude, we can find the angle, right? We can find the angle because this pail is moving straight up. It's not moving sideways. And so this right here, let's make that red or orange. That right here has to be the x component of force 1. All right, well, we can do that. So for theta 1, it's a 1 right there. We know for the force 1 is 7 newtons. We know force in the x direction, force 1 in the x direction, is negative 5.16 newtons. Now that negative won't really matter in just a second. We can use those to find what theta is, because after all, the magnitude, 7 newtons, times the sine of theta 1 equals the x component of theta. The x component of force 1, 5.16. That negative isn't going to matter because all we're doing is finding the magnitude of that angle right there. So just like we did up here, magnitude times the sine of theta gave us this. So we can use this now to find what theta actually is. So theta 1 is going to be, theta sine, let me back up here. Sine of theta 1 is 5.16 divided by 7. And then, of course, to find theta, we just take the inverse sine of that. So theta equals sine to the negative 1 of 5.16 divided by 7. And that will return for us what theta has to be for force 1. So 5.16 divided by 7, that gives me 47.5 degrees. And that is our answer for part A. In fact, I should have written A here, and I'll just put A right there. Okay? This is all part A. We're finding that angle. That's the angle that has to be right there. 47.5 degrees that force 1 exists at. Okay? Well, great. This is 47. Theta now, I'm going to erase that question mark there. Theta 1 is 47.5 degrees. 47.5 degrees right there. Okay, so that means now that we know, since we know this magnitude of force 1 and we know this angle, we should be able to find then the y component of Jack's force, now that we know the angle and the magnitude. So the y component is the magnitude, 7, times a cosine of theta. So 7 times a cosine of theta, I get 4.73. 4.73 newtons. That's important because part B is asking us, what then is the acceleration, the straight upwards acceleration of the pail? So the acceleration of the pail, that's what we want to know. But we needed to find that y component of force 1 because that'll help us sum all our forces together and find out what the actual acceleration is. Well, let's draw all of our forces on our pail. I'm going to go back to my dark blue right here. All right. We have the y component of force 1. Force 1 y. Oops. Y. We have the y component of force 2. Force 2 y. These y's are turning out for me. Okay, and then we have the weight force, which we didn't really need to calculate because we were told it at the very beginning. That's this right here. The weight force, that is the force that gravity is creating, pulling that mass down to Earth. So we want to find the acceleration of the pail. The pail, which I didn't write this, but the pail we're told is 1.30 kilograms. So the mass of the pail equals 1.30 kilograms. That's going to be important in just a second. So what we can say about this pail that's true is the net force on the pail is the mass of the pail times acceleration of the pail. Sorry, I didn't have space to write in pail, but you get the idea. This is Newton's second law right here. The net force equals mass times acceleration. The net force on any object is the mass of that object times the acceleration of that object. We have the mass of it. If we can simply find the net force on this object, we can solve for the acceleration. Here's how we do it. We can say, what's also true about this is the net force on the pail can be described as these three forces working either with or against each other. That means it equals F1. Sorry, I picked the wrong green. Oh well. F1 in the y direction. And by the way, that's positive. Plus F2 in the y direction. Both of them are moving the same direction upwards. Minus, and look at this right here, because this is the weight force is pulling downwards towards the earth, minus the weight force right there. All right, we can state that as being the net force in the pail, and then set it equal to the mass times the acceleration of the pail and solve for the acceleration. So that equals, I'm not going to change colors here, F1 in the y direction, that is 4.73 newtons, plus F2 in the y direction. We found that, that's 9.71 newtons, minus the weight force of the pail. The weight force we were told at the very beginning, which is right here, 12.8 newtons. Okay, so we sum all these up. This is going to give us the net force on the pail. I get a total of, what do I have here? Oh, you know what? I did it all at once. In fact, you know what? Let's do that. Well, no, I'll do it in steps here. 4.73 plus 9.71 minus 12.8. 1.64. There's a net force of 1.64 newtons on that pail because Jack and Jill are both pulling upwards. Gravity's pulling downwards, and they're pulling just a little bit more than gravity is, and so it's going to move upwards. That's good to know. So since the net force on the pail is 1.64 newtons, and we know the mass of the pail right here, we can solve for the acceleration. That is the acceleration of the pail, and this is going to get kind of tight down here, is going to be the net force of the pail divided by the mass of the pail. That's going to give us our upwards acceleration. The net force is 1.64 newtons. The mass of the pail, we're told, is, 1.30 kilograms. Newtons divided by kilograms is going to give us an acceleration, and that acceleration is going to be 1.26 meters per second squared. That's our acceleration of the pail. We found the net force on the pail, and we use that in conjunction with the mass of the pail to find the acceleration upwards of the pail. So there you go, example 6.3. Hope that helps. Using this net force scenario right here, net force is always equal to mass times acceleration, and net force right here is the summation of all those forces together. Setting these equal to each other is going to be a key part in solving problems like this. Okay, so we're going to look at this again in the next example. But for now, that's a great application of Newton's second law. Hope that helps. Let me know if you have any questions. I'll see you in class.